Okay, so very warm welcome once again to my YouTube channel. So today I will be doing the third tutorial of this open source CFD hands-on tutorial series. It will be about CFD simulation of a damper, which is enclosed in a duct. And I'll be using NGrid as a mesh generator and OpenFOAM as a solver. And the post-processing will be done using ParaView. So brief description, as mentioned, it is the third tutorial of this open source CFD hands-on tutorial series, and we will see how we can import an STL geometry, which will be the damper geometry, and how we can mesh this damper geometry within a duct with the use of an excellent open source mesh generator, which is NGrid, and how we can extract our fluid volume and export the mesh in OpenFOAM format. And then later on, we will be performing the simulation by using this incompressible flow solver with the help of OpenFOAM. A brief disclaimer before I really go on with the actual stuff. So NGrid is being developed and maintained by NGrid's GmbH, and it is licensed under this GPL version 3.0. If you're interested, you can have a look on this one. And OpenFOAM and OpenCFD are the registered trademarks of OpenCFD Limited, so which is the producer and developer of OpenFOAM software. So all the registered trademarks are property of their respective owners. As I have already shown this slide several times in my previous tutorials, so NGrid is an open source mesh generator, and these are some of the features of this excellent mesh generator, and this is the download link, which I will also post it in the description section. So if you're interested, you can download this software. So today's video session scheme will be as follows. As always, I'll be starting with with a live demo with combination of the slides, giving you the brief or important information in terms of the slides, and then we will use this information to apply it in our meshing and CFD solver settings. So I'll starting with the meshing approach first of all. So this is the meshing section. So we will start with the meshing. Starting from importing the geometry, and then we will assign the boundary patches later on, which will be used as boundary conditions, and we will be performing our hybrid meshing. As we can see, the damper, and these are the walls of the duct, so we'll be using kind of an hybrid, so a viscous mesh. Later on, I will also show you we will be extending upstream and downstream of the damper some extensions in both directions, in the damper upstream and the damper downstream, in order to really have a fully developed flow. And after the damper, so after downstream of this damper, there will be flow separation, which we will observe later on. So really to avoid any kind of undeveloped flow or any other artifacts. So the first step will be to import the geometry and assign the boundary patches and for the fluid domain. And we need to first of all check the surface integrity, meaning that if the geometry is okay. Second step that will be after importing the geometry, which will be followed by the assign boundary patches. So it's like the left duct underscore left part and the duct underscore right part. These are the inlet and outlet patches. And the front part, which will be the symmetry, because I'm just modeling half of the damper geometry. So the front part, which will be the symmetry part, is not shown here because it is really normal to the plane. That's why I have used this view to show other parts, so which is enclosed within the duct. We'll be having the bottom, top walls, back walls, and the damper walls. So we will be using no slip boundary conditions on damper and duct parts, so the patches which is mentioned here. Duct front will be the symmetry part. So these are the surface meshing parameters. So I'm using a maximum edge length of about 0.1. And as always in other meshing tools, if you're using Snappy Hex Mesh or using other commercial meshing tools, you always have the option or privilege to perform local mesh refinements or surface refinements. So NGrid is also giving you this option, so which is in the form of rules for mesh resolution. So I'll be starting, first of all, I will show you how you can improve the overall surface mesh of the damper, and then in the next step we will be trying to improve the edges, surface edges of the damper geometry, as we can see in this mesh here. And then we will move on to the hybrid meshing. So in other words, we will be generating our complete tetrahedral plus prismatic layer of cells combination, and to form a fully complete volume mesh. So we will define first of all the volume zone, and then we will specify the prismatic layer parameters and choose the specific patches on which we wanted to generate our hybrid mesh or the prismatic layer. And after defining the prismatic layer, we fill in the rest of the fluid domain with the volume mesh, and then as the process is really set up in a way in NGrid that you start first of all prismatic layer. First you define the complete total boundary layer thickness, then you define the volume mesh, which is shown here in the red color, and then once you have this tetrahedral end prisms connected, and we will then refine our prismatic boundary layer. Later on we will be doing the mesh extrusion. So we will take, for example, this duct underscore left part, which is the inlet, and we will extrude. So in order to really have, so we'll be extending our inlet, duct inlet on the upstream of the damper, and similarly we will be doing after downstream of the damper further extension of the mesh. And it's really quite a cool feature in case of really complex geometries. So if you don't want to do or fill your complete fluid domain with triangular elements, you can just locally mesh it with the combination of hybrid elements, like it will be tetrahedrals and prism layers, and the rest of the domain with the help of extrusion feature. So you can extend your domains, and one will also get very good convergence. Okay, so these are the steps which I will be using to now generate our mesh. So I would say now let's move to the real part. Let's move to NGrid and apply all these steps. Okay, so if you have already watched my previous tutorials using NGrid, you might be familiar with this GUI. So we will be first of all importing the STL geometry. So it is this damper. So this is the tolerance. We are happy with this tolerance, let's say. So this is how the geometry is looking like. And we can see on the left side is the output section or the output window. Right side we have the display options, which is used to like show surface elements and volume elements. So first step we need to do that, we need to change the surface orientation. It's kind of recommended in NGrid that you really make sure that the outer surfaces are like in green in color. So either you can change the surface orientation by using the shortcut key, or you could go to the mesh and you say change the surface orientation. So if you click that, and once you move or click in this working window, it will show you this color. Now if we press on our keyboard V, the V button, or if we go to the view and we say boundary codes, so we're just seeing at the moment one patch with an ID of 999. That means they are not defined. So what you normally do here is that one should just hover or select the patch. For example, we will be starting from this left side. That will be our inlet, and that will be our right side. That will be our outlet, and the front portion, which will be our symmetry boundary conditions. So I will just hover my mouse on this inlet patch and press P on the keyboard. You will see this red circle or this red sphere, meaning this patch is selected. And then you select, after selecting this patch, you will press S on the keyboard, or you can press simply set boundary code. And we will go and you will say, I would like to start from boundary number code number 1. So this is something that one should really plan before that, or while you are doing it, you just note the numbers. So the boundary code number 1 belongs to the inlet or the duct underscore left. So once I will define that, it's like hidden. This means this is now defined, this patch. So I will move on to the outlet patch. So normally the approach which I always use, I use inlet, outlet, top, bottom, front, back. So this is the kind of patch defining or assigning scheme which I always use. So you need to be consistent and stick with one scheme, and there should not be a problem then. So I will select now this part with the same approach. I will press S on the keyboard, or I can go through this boundary code. I will say this will be the patch number 2, that is outlet. So we have inlet, outlet, then we will go to the top part, press P on the keyboard, S again on the keyboard, and that will be the number 3. So it is now our outlet and our top boundary condition. We will go to the bottom part, press S, define, give the number ID. It's now done, and then we will move on to the front part. This is the symmetry. So press S again. So we will be giving the boundary code number, which is 5. Move on to the back part. Press S again, and then define the boundary code, which is number 6. Now we are just left with our damper. So if you want, you can define one boundary code and select all the patches one by one, and always give the same boundary code. So then, for example, if the next one will be now number 7, so number 7 will contain all the patches of the damper part. But I will be using deliberately different patches, patch ID numbers for each damper surface. That will help us in performing mesh refinements. For example, the damper edge refinements, as already shown you in the slide, and later on we will be doing surface mesh refinement in the vicinity of this damper. So let's start from the left part. So select P, and I will say number 7. So remember now, up till number 6, we are having the outer part of the duct. These are the patches. Now from number 7 onward, we will be starting with the damper code boundary patches. So 7, this is the inlet, this is the left part of the damper. So I will hover the mouse on the right part of the damper. Again, define the code number 8. So always left, right. Then we have now top, which is this part. Okay, so this is number 9. Then we will go on to the bottom. This is number 10. And the last one is the damper back patch. So okay, right, so we are now here done. Now if you press V on your keyboard, or you can go from view boundary codes. So we can see we have already defined. So if you remember your numberings, so number 1, 2, it's like inlet, outlet, top, so duct, so left part, right part, top, bottom, front, back. Okay, and then we start with the damper part. So, and now I will show you how we can change or manage the boundary conditions, or change the names of the boundary conditions. So we start with the one, first of all, duct underscore left. So that will be the patch. It will be the inlet boundary conditions. The duct underscore right. That will be the outlet boundary condition. Then we will start with duct, so left, right, and then we have top. We have bottom, and we'll be having duct underscore front, so which is the symmetry patch. Duct underscore back. It will be again a wall. And from here, starting with the damper. Damper underscore left, so damper right, damper underscore top, damper underscore bottom, damper underscore back. So this will be treated as a patch in OpenFOAM. So these two are the patch boundary conditions, and the top one is a wall. The bottom one again will be the wall, because we will be generating prismatic layers also on this boundary, so it will be treated as mostly boundary conditions from the duct part too. This is a front part, so it is treated as symmetry boundary conditions. So the back one is again the wall. So all the damper patches will be treated also as the viscous boundary conditions or no slip. So okay, so inlet, outlet, and symmetry. We will say okay. Now we will start our surface meshing. So you click on this edit surface meshing parameters. You have seen in the slide, so I'll be using maximum edge length of about 0.1. Now surfaces to mesh, so we will be meshing all the surfaces. So select all, and we have some certain rules for this one. If you remember in the slides I've shown you. So these rules will be like this. Yeah, so we say we wanted to have a surface meshing over the whole damper patches of about 0.05. So we have a global maximum edge length is about 0.1, and we will see the difference once we will mesh this. So once we define our surface parameters, so I will say create and improve surface mesh. So these are kind of default conditions or settings which should be okay. No, most of the cases you need to run this twice to get a decent surface mesh. So let's first of all just start with this one. You see it's really very quick, it's already done. So this was the 5th iteration. And another important thing to note down is the change ratio. So during all the iterations, you can judge that there is a mesh is changing or not by using this change ratio and the fluctuation rate. So after it is finished, when you simply click in this working window, you will get to see your mesh. So in order to get some better idea, I will press once again V on the keyboard and simply hide the front or the symmetry portion to have a better look on our fluid domain. Now I will perform the mesh again so that we can see the difference of our surface mesh refinement on the damper and the rest of the domain. So now it's finished. You see it's saying it's the end. So once I will again click in the working window, I will get my final surface mesh, which is now kind of okay. So we can see it's like 0.1 cell sizes, and this is a half of this 0.005, which can be seen very easily here. Now we will be using like edge features or edge refinement. So we will say the damper top part and the damper back part, similarly the right part and the damper. So all these edges which will be accessed with the combination of damper surface patches to really define a surface mesh refinement. So I will show you how we can perform this. So we will see now how we can improve the damper edges. You will go once again to your edit surface parameters, and we will go to the rules of mesh generation, press enter, and we will be saying so the damper left patch and the top, the right patch and the top, so from left and right, which has like intersection, so it has the top patch, so that it will detect the edges, right? And we'll be defining a little bit finer mesh refinement edge length. So let's say okay, and we will perform once again our surface meshing operation, and you will see that NGrid will perform based on our rules for mesh generation which we have defined. So all these patches or the periphery or the boundaries of the meshes, it will detect the edges very smoothly, nicely, and it will define the mesh. So it's now done. You will click again in the working window, and you can see that the edge mesh refinement has been done very nicely. So you see this one. So it's the top part of damper, it's the left part, and so we have defined so left and the back part, similarly with the top. Similarly, if you can see also on the bottom part, the mesh refinement has been achieved quite nicely. Now, before we really go on to perform our volume mesh, another important step which is to be performed is we will be doing kind of a volumetric mesh refinement or in the vicinity of this one. So we will be defining some geometrical source to perform a mesh refinement in this region. So because this is very crucial, you will be having very strong gradients in this region, and in order to resolve the mesh in the vicinity of this damper, I'll be using a geometrical source. And so how you can define this one, it's a similar approach. For example, if you are using any commercial code, you normally define your geometry and use this geometry as a mesh refinement tool. Yeah, so it's similar to Snappy Hex Mesh, where you use some standard shapes like cylinder or sphere or a rectangle, all these kind of tools. So you will go once again to the edit surface parameters, and then you will go to the sources tab. You will say add cone, so it will come up with some standard name, default name. So you click then on, after selecting this source, you will click the edit button, and we can actually rename that. I will call that for example cone damper. So I'll be using these coordinates to perform or generate this cone. Similarly in minus 0.339, so in the y direction we'll be using the same coordinate, and then minus 0.339, so there is 10 more, and we will be using this mesh or edge length, and this is the radius of our cone, so of both sides of the cone, 0.03. So this looks good. Alright, so now after we have finished, then we will go on to perform once again the mesh refinement process, and you will very soon see that there is a mesh refinement in this vicinity of this damper. So as we have defined our cylindrical or this cone in this region. So almost done. Number 3. And we know that there is a change ratio. This is always continuously changing, and the fluctuation ratio. So from here you can judge that there are changing happening. So now we will move on to the last surface mesh iteration, which is the 5th one, and we will be able to see the difference quite clearly. So it's now done. So once you click it, you see, and you can see the impressions of the cone and the mesh resolution, which with some finer elements can be seen in the vicinity of the damper. So it's totally around this damper, right? Okay, so till this step, it's we are really happy with the surface meshing, and now the next step we will be moving on to generate the volume. How you can generate the volume is, first step will be, first of all, you will be generating the prismatic boundary layer. So if we select once again all the patches first of all, so our inlet patch, our outlet patch, and the front, which is a symmetry patch. Except these 3 patches, all other we have defined, if you remember, in our boundary conditions as wall. So we'll be using a no slip boundary condition on that. But before we really move on to create our prismatic boundary layer, there is one very important thing. First of all, we need to define the volume. So how do you define the volume? You go to edit boundary conditions, you see, and then here new volume, you will say volume. So I will say then add, click add. So this volume is added, and this is the name of this volume, and this is assigned to this surface mesh. We will press OK. Now if I go to this patch, I can select this volume, right? So I will select once again all these patches excluding these 3 patches. So our left, right, and front part, and we are happy with the default settings. Normally this should be okay, because since we are not using any absolute height, so we could say simply 1. So I'm just at the moment trusting in just for the demonstration purposes, relative height of the first cell, which is based on your local surface mesh. If you are really using, I would say, if you wanted to have a y plus value of exactly really 1, or doing some specific test cases where you don't want to use kind of a high Reynolds number, let's say turbulence models, you should then define not relative, your absolute numbers, and if you are really looking to use low Reynolds number models and you wanted to get y plus of 1, and you want to resolve till really the end of your viscous wall. But normally, even for doing different kinds of computations, with my experience, you normally really getting very decent y plus values also if you really settings are okay. So now we press OK, and after doing some internal calculations, it will tell us that NGrid will be performing or seeding so many prismatic layers, and it will perform 10 number of iterations to improve the prismatic layer. Okay, so I will show you in a matter of time once the total prismatic layer or the total boundary layer thickness is finished. You see, it's already telling us it is seeding like about 12,722 prismatic layers, and it will take about 10 iterations to finish it. Okay, now we are now finished with our prismatic mesh layer generation. So in order to really see that, we need to first of all turn our symmetry plane on, you see, and it's kind of can be seen properly also if I now orient it in proper view. So this is the duct boundaries, so wall boundaries, and this is the damper part. So if you really wanted to see the volume, since we just generated the prismatic part, so you turn or disable the surface elements and refresh and fit to the screen. This is how our prismatic layer mesh or the volumetric volume mesh looks like. Now we are finished. After defining the volume zone, we have generated the prismatic layers on the viscous walls. Now we will be using the create improve volume mesh option to generate the mesh. So the rest of the domain will be filled in with the tetrahedrals, yeah, in case of 3D. So it will take 3 number of iterations. So once it's finished, I will show you the volume mesh. Okay, now it's finished with forming the tetrahedral volume elements. So now the volume tetrahedral elements are connected with our prismatic cell. So the final step to finish the volume mesh is to now refine the prismatic boundary layer, which is this one. So we will now divide the prismatic boundary layer. We will say volume. So it is now the default options are like to 11 number of layers. As mentioned also earlier, we will stick to the blending in terms of we will just using so relative one, which is 0. If you wanted to use an absolute values, you need to specify this parameter. Okay, so rest of the stuff which should be okay. And now for this tutorial, for the demonstration purpose, I'm happy with the default setting, and let's say okay. All right, so now it is finished totally. Now dividing the prismatic boundary layers to 11 number of layers. So we can see this was the total prismatic layer thickness, and NGrid has divided now the total 1 layer into 11 number of layers, and the first cell thickness is like very small, and then it grows on based on your stretching ratio or your aspect ratio function. So till this point, we're really happy with our volume mesh. And now what we will do, the final step is to perform mesh extrusion. So we will be extending the downstream and the upstream length of the domain. How do you do that? You go to this option extrusion on the shortcut, or you can perform it from here, and then you need to say that you need to extrude. So you can also access this option from mesh and extrusion menu. Okay, so we'll use this one, a shortcut. So I will say first of all the left duct. So I will perform about 20 number of layers. I will say total height of the first layer is about 0.12, and increase factor will like 1.11. So it starts a little bit finer and then it keep on increasing till it reaches to this 20 number of layers. And it's in the X direction since surface normal option is on, so you don't need to really worry about the sign of your direction. Okay, so our inlet surface is now selected, 20 number of layers. We have our first height of the first layer is defined, increasing factor of 1.1, and we will say okay, and we will be able to see a very nice extrusion of 20 cells upstream of the damper in a few moments. So it's now done. So we just need to wait a little bit. You see, if you fit to the screen, and I would say like this one, now you can see that. Yeah, it's a really nice transition of elements from this to this, as you can see, based on the inlet patch, which is this here. So the prismatic layer matches really pretty well, and also it's really fully conformal mesh. So it's not really a non-conformal mesh. With this, in that case, you have really irregular nodes on the interfaces. So it's really matching very well. And the same approach we'll be using now to generate on the right side. And you can also see in the boundary codes there is an addition of another patch with this ID 12. I will show you later on how to manipulate this one. And we will be actually merging these patches into the existing patches. We want to avoid really a lot of several patches. So we will be using the existing patches and merge these patches into the existing one. So we will use now the outlet, which is the right one. So I will say total number of layers 50, and I will use the same height. Since this is the downstream one, it's like just behind the damper. So I would like to stick with the constant increase factor. We don't want to change that, because if there is any kind of flow separation effect or like this, so I would like to resolve that properly. Okay, so I don't want to get rid really of these effects and dissipate them very quickly. Okay, now it's fine. So let's say okay. And we'll see in a few moments that similarly so now if you fit your screen, yeah, you can see we have an inlet patches, so extruded, and now similarly as we have seen upstream of the damper, downstream of the damper, the meshes are really conformal, and even on this extension part, this interface where we extruded our mesh, is really working very fine. Okay, now I have mentioned, okay, let's get some more space. I will close this output window for the moment, and maybe this one too. So you can get some more space here. So if you press now V on the keyboard, we are having now two new parts. Okay, so the trick here is like that I will be, first of all, you need to, if you go to the view options and display, show the display options once again. So I need to disable the volume elements option and turn this on. Once I have the volume options on, the surface options on, you can see by default we have like two surfaces which are not shown here. So if I turn them on, see, now it's showing that. So the trick here will be that you note down the existing patches, or you know already the ID, the boundary codes. For example, let's say we start with the front patch. We know already that the duct underscore front one is the number 5 ID. So since these two unknown parts are showing the complete duct patches upstream, and similarly the downstream part. So what we will do, we will now try to define these patches to the existing patches. Okay, so let's see, I will say this is number, the front part is the 5, so I will press P on the keyboard, Now I will go here and I will say I want to define this patch to the existing patch, which is a symmetry one, which is number 5, right? So it is now defined to the number 5. So this is already the symmetry part. We can identify very easily because this has this triangular mesh. Now we will go downstream of the damper, again press P and say I will use same part. Okay, now same boundary code ID. So I will show you now. If I turn off the front part, you will see that the complete patch is now been defined. So it consists of all the complete, even including the mesh extrusion patches from the symmetry part. So the similar approach will be used to define the other patches. Okay, and once we are really done with it, then we will extrude our geometry in or export our geometry in an OpenFOAM format. Okay, so now I will try to do it a little bit quickly. So we have defined our front part. So the back one is the number 6. So let's say we start with this part. Okay, so if we now the back part, turn it off to see it's really working fine. Similarly, the top and the bottom parts. So let's start with the, okay, we need to first of all get the number for the top part. So this is number 3. So we have our patch selected. We will define it to number 3. It's defined here. Go there, select this side. Number 3, it's done. Now if we disable the hide this part, it's okay. Now the bottom part, so you define that. We will say, I think the bottom part is number 4. So you select this part upstream, number 4. Number 4 is like done here, the downstream part of the bottom patch. Okay, all right. So if we now hide this part, it's looking perfectly fine. So the inlet and outlet is not really changed. We're happy with that one. You now select all. So all the boundary patches are properly defined. And now the last part is like if you go to the edit boundary conditions, it's like completely done. And before you normally go, so you need to manage your boundary conditions that later on when the OpenFOAM grid is exported, so it will be based on these boundary conditions, it will be exporting your grid. So wall is like wall. If you have an inlet, so it will be like inlet. And then similarly, if you wanted to use an outlet one, so you use an outlet. So this is just kind of a, for the sake of completeness, I am doing it. So symmetry, you will say add symmetry to symmetry. We are happy really with these settings, and once you are happy with that one, it's now okay. So the final step will be like you go there and export your mesh in an OpenFOAM format. We're just interested at the moment in just in grid. So if you press OpenFOAM and grid only, so if you select the damper folder and then you say press OK, so your mesh will be exported. Okay, so I think till that point it's about it with the meshing part. Now I will come to this OpenFOAM solver part, how to really define the boundary conditions and how to set up the CFD simulation. Okay, fine. So we have now successfully exported our grid in an OpenFOAM format. Just to finalize once again, so the resulting mesh we got, it consists of about 534,000 elements in total. And if you really split it up, so this is the number of tetrahedral cells and prisms and hexahedrals. So now we will move on to the OpenFOAM part, how we can solve this and which settings are normally required. So I will be following this setup scheme as I did it in case of the meshing part. So we'll start how to set up really this steady state incompressible flow using a simpleFoam solver, and turbulence modeling will be carried out using the K omega SST, which is a two equation turbulence model. So it will be a steady state flow, and as mentioned earlier, we will be using incompressible simpleFoam solver with K omega SST. And as inlet boundary condition, I'll be using velocity inlet at the duct underscore left patch. If you remember in the meshing part where we have assigned the patches to the duct or the fluid domain, so we have defined the duct underscore left as a patch, which will be a velocity inlet. So 2.5 meters per second will be the velocity. And this will be the overall OpenFOAM directory structure for our test case. So this is really standard, and throughout any test case which you will be like performing a CFD analysis in OpenFOAM, it consists of these paths or these folders. So this is the main folder, which is damper in our case, and it consists of 3 files. So zero folder is like it consists of all the boundary conditions for your patches, and then there is a folder which is called constant. There is a subfolder polymesh where your grid resides. That is our exported grid. And then we have 2 more files in the constant folder. So since it's a viscous simulation and transport properties consist of this information, and then there is a turbulence properties file. We have the third folder, system folder, which consists of 3 files like control dict, where you really specify your number of iterations and writing intervals for your simulations. Then we have FP schemes and FP solution, which controls the numerical scheme which you are using, and the residuals and the solver you use for your simulation. So if you really go deep into the constant folder, the transport properties file consists of this information. So this is the kinematic viscosity I'm using. And then the turbulence properties file consists of the type of simulation you are performing. So I'm doing a run simulation. That's why it says here RAS. And I'm using a runs turbulence model, which is K omega SST. So the turbulence parameter is also on. That means we'll be solving a turbulent flow. So print coefficients mean if you turn it on, it will turn on the empirical display in your terminal, the constant empirical constants of your turbulence model used. So before you really start with your specifying the boundary conditions, it's just I would really like to emphasize here, just make it a standard practice that you make sure that for each test case or each application area where you are performing your simulations, to calculate the initial conditions, right, which is really important. For this will lead to better convergence, and this will lead to real physically solving the problems really well, and you will get some accurate solutions. So in order to get these initial conditions, there are equations available. So how you can calculate, for example, in our case, we are using the K omega model. So how to calculate the turbulent kinetic energy and the turbulent specific dissipation rate, which is this omega here. So and in terms of K epsilon model, if you are using a K epsilon model, you can use this epsilon equation. We are in the above equations, the L is the turbulence or eddy length scale, which is given below, which is mentioned here, and C mu is a turbulent constant. So its value is about 0.09. And this capital I, which is used here in turbulent kinetic energy, is the turbulent intensity. So as mentioned here, capital L is really a characteristic length scale. So if you are using a pipe flow or internal flow, it could be your diameter, hydraulic diameter. If you are using a car or a ship or an aircraft or airfoil or wing, it will be the length or a chord length of your airfoil. Yeah. So if you are interested, you can further go also for this link. I've also mentioned it here. If you wanted to do or read further, if you are interested, go ahead and have a look. So for our test case, the damper one, I have a reference length approximately about 1 meter. This is the kinematic viscosity, and C mu constant for the turbulence model. This is 0.09. We have a velocity, inlet velocity of 2.5 meters per second. So these are the inputs required to calculate these values. So Reynolds number, turbulent intensity, and turbulent length scale. So this is our Reynolds number. So it's about 156,000 or approximately 157,000. So the flow is really turbulent, and the turbulent intensity based on these input calculations is calculated as 0.71%. So the turbulence length scale is like this. So once you calculate all these values like Reynolds number, turbulence intensity, and length scale, so these all will go in to calculate your K and omega values. Okay. So based on these assumptions and calculations and inputs, we end up getting our K and omega values for our test case. So once you calculated these values, you will put them in your equations or the boundary condition files, which resides in the 0 folder under your damper folder, if you remember our OpenFOAM directory structure. And then you will specify, and accordingly we will define the boundary conditions. So everywhere we are using like wall boundary conditions or no slip boundary conditions, we'll be using omega wall function, except for the input, which is the left part, we'll be using fixed value, and the right part will be simply sticking with the zero gradient. That is like the pressure outlet part. And for the symmetry, you stick with your symmetry boundary condition. And then we will move on to the turbulent kinetic energy file. Similarly, we'll be using our calculated value for our initial conditions, and we'll stick with the same approach like all the no-slip wall boundary condition or patches. We will define the wall function as a type, and we will initialize the inlet patch with the fixed value and the pressure outlet, which is the right part, as zero gradient, and symmetry will be sticking with the symmetry part. And now we will move on to the eddy viscosity, so nu T. So same approach. In that term, we will use for both inlet and outlet as zero gradient, and the rest of all the walls we will be treating as nu T U Spalding wall function. And for the pressure part, we say initially the pressure is like 0 everywhere in the flow field, and then we are using a fixed value which is about uniform 0 value. That is like you are applying a pressure about 0, so that it has been assumed that your outlet pressure cancels out as it compares with the atmospheric pressure. So the rest of all the wall boundary conditions are treated at zero gradient. Once again, the duct front patch will be our symmetry plane, so we'll be using the symmetry boundary conditions. So the last one file is the U, which is for the velocity part. We initialize our flow field with an x velocity of about 2.5 meters per second. And all the viscous or the no-slip boundary conditions is applied on all the patches, except for the inlet part. We define an inlet boundary condition with the x velocity of 2.5 meters per second, symmetry boundary condition on the front patch, and the right one will be taken as zero gradient. Okay, the most important folder, which is the system folder, it consists of 3 files. The first one is the control dict. So you specify your solver which you are using, and then you say I'm starting from. So normally I stick with this latest time because if you have somehow stopped somewhere or you want to run further, so instead of really getting overwritten with the new simulation startup, so normally if you put it like latest time, so if you end up from the last simulation about 300 iterations, so it will start from the 300 iterations onwards. So it will not start always from 0, even though if you even set it here start time 0, if you're just running for the first time, it will start from 0, but afterwards it will start from the latest time interval which is available in your folder. And I'm using an ASCII format as a standard practice. Write precision is about 10, and rest of the parameters are really default. So we will move over to the FV schemes file, which will tell you about which schemes we are using as this is a simpleFoam solver, so it's a steady state solver and for incompressible flows. So for the derivative for the DD schemes, we'll be using steady state, and to resolve the gradient schemes option, I'm using this setting, which is more of a standard settings where for most of my cases. Similarly also for the velocity, k and omega, and the divergence schemes, I'm using Gauss linear as a default, and the rest of the settings you can also see here. I'm using a linear interpolation schemes. So as a wall distance, I'm sticking with the mesh wave method. So the last one is the finite volume solution. So FV solution file, so where you normally specify the solvers which you are using. I always prefer to use this GAMG. So it's a multi-grid solver which is really good to solve the pressure equations. If you have some trouble with the convergence, you can switch to the other one like BICG stab or PBICG stab, which is the one I'm using for the velocity, turbulent kinetic energy, omega and phi. That I'm using GAMG once again. I highly recommend using always this to run about 10 north orthogonal characters. Like you should run maybe 10 or 20 iterations with your potential flow prior to starting with your real simulation. This will help in the convergence. So, and the residual controls and selection factors parameters are shown here. Okay, so now I think let's move to our simulation part. So I have already shown you the settings we will be using for our setup. I will now move on to show you and start with our simulation. So I have already set up this our OpenFOAM damper simulation stuff. As I'm using OpenFOAM in Windows environment, so but you can use any other operating system whichever suits you or you are already using, so you can use that one. So first of all, let's check our boundary file, which the grid we exported. So if we really see now, so in total there are 11 patches. So it starts from duct underscore left and duct underscore right. So this is our inlet part. Right, it's a patch. So we can see that NGrid really exports all the patches in properly specified format because we have explicitly assigned the boundary conditions. So it's all been really done properly. Yes. So that's looking really good. So as mentioned, I will start first of all with the potential form to run about 10 iterations. Let's make a log file of that. Potential form. So it will take a few moments to start the iterations, and once it's really done, then we can move on to the real part, like starting with our simpleFoam simulations. So we can now see that it's been now solved for about 10 number of non-orthogonal correctors. So we see with the number of iterations increases, the convergence really improves, and it has been solving for phi. So this is the continuity error, and the interpolative velocity error is like approximately e⁻⁻⁶, which is really looking good. This really helps us in starting with the real simulation. So let's move with the simpleFoam solver. Okay, so we start with our simpleFoam. All right, so now it's the simulation is really started with simpleFoam. So I think it will take about 1000 iterations. So let's see how the convergence goes on, and I will share with you guys just later on how it really comes out, the total convergence. So then see you in a few minutes. So, all right, if we can now see that the convergence after about approximately 850 iterations, it looks really good. So I just thought of sharing with you guys the convergence. So we can see that overall it's really a good convergence. And if we really see the results after approximately about 1000 iterations, so there are two plots. So I'm just taking, let's say, a slice within the domain, so normal to the y-axis. So we can see on the top you are seeing the velocity in the x direction. On the bottom part you are seeing the flow behavior around the damper. So that's the pressure, and we can see really that even with our mesh, which is really kind of a not really a very fine mesh. It's kind of in between coarse and medium, you can say the trend is, but there is still a tendency to really go for further mesh improvements, and especially just behind the damper or the downstream of the damper part, because we really have a very large domain. And but on the other hand, extension of this domain in the upstream direction and also in downstream really helps also not only the convergence but also to get really of developed flow. So we can even change the velocity to, so let's say to velocity magnitude. So if we turn this on, and we can see this is how it really looks like, yeah. And another thing you can also notice that I have a linking of the frames. So if I zoom in one frame, so it's really linked in. So this is really a very nice feature even in ParaView. So one could even compare 2 or 3 different frames or windows together. So you are not really worried about the scaling, the physical scaling of the models. And we can see this this large separation behind the damper, which is really expected. If we really increase the velocity, this might be much more aggressive. We can see, and the pressure building here just before the damper, there is really a high pressure, and then there is an increase in the velocity. Which results in a lower pressure. So you can see even there is a negative pressure, which is about minus 20. The value here is, and yeah, I think this seems really promising, and we can also say that this simulation really converges very well, and the approach of using, let's say, tetrahedral meshes in the vicinity of this damper, and further as you move further away from the damper, from in the upstream part and in the downstream part, you should use maybe this hexahedral cells with the extrusion method I have shown you in NGrid. So I mean, this is just for the demonstration purposes. Obviously, if you really have the computational resources available, you could increase it, and if you wanted to run it on a cluster, you can then run all your computations on cluster, and you will obviously get an improved simulation. And one could even perform a grid convergence study to see which mesh is really suitable for such type of flows. And we have also seen here that the K omega SST turbulence model, which is really popular for really separated flows in separated region, it's really performing well. One can also do turbulence model study, so you can even use K-epsilon turbulence model or Spalart-Almaraz to really get in comparison and see what kind of effect is coming up. Maybe you can do some slices downstream of this damper in the flow separation regions and compare this velocity profiles and pressure profiles, how it really looks like. Okay. So if we really now conclude our video session, we can really say that the very nice convergence has really been achieved. And we can also see once again, this is one snapshot of a velocity contour. And there it can be seen that accelerated flow is really coming in these regions. So just these small channels which is not been covered by the damper. So the incoming velocity is coming from this side, and you have a flow acceleration, and then just completely behind this damper there is large flow separations accepted. And so you have like pressure contours as we have already seen in ParaView recently. So you have a high pressure region, and then you have a low pressure region. Obviously this region is really affected with the flow separation, but here it can be seen that there is a accelerated flow in these regions, and we are using our no slip boundary condition, and we have resolved the wall properly with prismatic layers, the damper and the duct top at the bottom parts. And if we really see that the turbulent kinetic energy, so it's also following the similar trend. If we really see this part of the velocity, and in the end we can summarize our today's tutorial session, that we can claim now that how to really mesh the model within NGrid. I think I have tried my best to really give you an overview and deep insight how you can mesh different types of geometries. So if I really take into account the previous 2 tutorials also, which I have done it for an exhaust manifold, I have used it for a blunt body for external aerodynamics, so internal flow, and then once again this damper which is enclosed in a duct, so it's kind of a combination of both your internal and external part one could really take into account, and how we can assign the boundaries, and finally after getting a nice volume meshes, how you can export your grid using NGrid in OpenFOAM format, how to set up incompressible turbulent flow within OpenFOAM. And we can say, having a look at our residual plots, our solutions, that the solutions really converge successfully. So with this, I conclude my today's video session. Thanks a lot for watching my tutorial, and I think that's it from now. And don't forget to subscribe and like my channel. I need you guys' support, and keep supporting me. And in case you want me to do some specific tutorials using OpenFOAM or NGrid, or maybe some other stuff, just let me know in the comment section. And until next time, with a new video, with a new topic, have a nice day. Bye-bye.